Another example I want to look at is the potential for conductors. And I want to highlight the fact that the electric field being zero does not imply that V equals zero. It just implies that V equals constant. So I want to emphasize that. So we're going to look at a charged conducting sphere in equilibrium with a radius 1 meter, a charge of 1 coulomb, which is going to distribute itself on the surface because we are required in equilibrium for the electric field inside the conductor to be equal to 0. So, if we're going to look at the electric field for that, E 1 over 4 pi epsilon naught Q over R squared for values greater than 1 meter, the electric field is going to die off as 1 over R squared. For values less than 1 meter, E is going to be equal to 0. So in this case, the electric field at the surface would just be 1 over 4 pi epsilon naught times 1 coulomb divided by 1 meter squared, which is just going to be 9 times 10 to the 9th volts per meter, or newtons per coulomb. And then it's going to die off as 1 over R squared. Notice this gets rid of the infinity with the electric field, so a way to get rid of it might have been if atoms had turned out to be small conducting spheres. Turns out not to be the case. We have to have another way to get rid of our infinity, but that would have worked. It just turned out to not be correct. So our V is going to be 1 over 4 pi epsilon naught Q over R. At the surface, that gives us 9 times 10 to the 9th times 1 coulomb over 1 meter, leaving us 9 times 10 to the 9th volts. And remember, E is not changing, and therefore the rate of change V is 0. But the derivative of the constant is still going to be that. So that gives us a value here of 9 times 10 to the 9th volts. Then that's going to die off as 1 over R. I tried to draw it so it's dying off a little bit slower than 1 over E as we move away from our radius at 1 meter. This is another set of data that was created in lab using 2 planes with a circle in the center. So what we have here is the conducting circle has a constant electric field. Right, the rate of change is equal to 0. The value is not equal to 0, but the rate of change is equal to 0. And then outside of that region, it drops off very quickly. It dives into it very quickly. You get this sort of curving around. But the important thing to note from this one is that the voltage is constant, and therefore d by dx of our potential function is equal to 0, since V is equal to a constant. But it's not required to equal 0. A practical application of these concepts is less common now, but in old-fashioned TV screens, there would be a pair of accelerating plates. The electric field would point leftwards in this picture. A bunch of electrons would be created by heating a metal wire, and then they would be accelerated between the two plates, controlled by magnetic fields, which we'll look at a little bit in future chapters, strike the TV screen, etc. So this area here is called the accelerator. It is a very, very small particle accelerator. So until probably about 2000, 2005, everybody had one or more small particle accelerators in their house.